Hello, I'm João, one of the authors of Entity Name Extraction from Faculty Directories. This poster was accepted at the Joint Conference on Digital Libraries in 2018, and I'm going to show you now a quick slide presentation. Public bibliographic databases hold invaluable data about the academic environment. However, research affiliation information is frequently missing or outdated. For example, in the DBLP database, affiliation information is missing for close to half of the authors among the top 1,000 authors with most published works. Well, our question is how to acquire this affiliation data. We may be able to extract this affiliation information from the front pages of research papers. However, it is not always easy to obtain access to a large database of papers. Another solution is extracting this information directly from university web pages. However, collecting this information manually is tedious and error-prone. Therefore, we need an automatic method. First, I'll show you a typical faculty page. This is a staffing faculty page of the School of Informatics, Computing and Engineering of the Indiana University. And this will help us show how some straightforward solutions may not achieve the desired performance. Well, we first tried an exact matching strategy. Since we have access to a lot of researcher names on DBLP, we can simply extract sequences of tokens that match a name exactly. So, how does this strategy perform on our previous example? It extracted 194 names. However, it only extracted 182 correct names out of a total of 388 names. So this strategy usually has a very high precision, above 90%, but a low recall. We can probably do better than that. Next, we tried a partial matching strategy. To improve recall, we considered a more flexible strategy. This time we extracted all tokens that occurred at least once in the DBLP name list. So let's see how it performed. It extracted 473 names and 358 from a total of 388 names. So this time we only missed 30 names. However, we extracted a lot of junk together with the correct names. So we improved recall, but precision got a lot lower. Perhaps we can achieve a better performance with a more sophisticated model. This problem is not so different from a named entity recognition task. So we employ here a maximum entropy model and extract all entities tagged as a person. In this example, we use the NLTK Python library implementation. It extracted 396 names and 23 correct names from a total of 388. So we missed 365 names. Both precision and recall were below 6%. The problem here is that state-of-the-art NER algorithms work well for plain text, but not so much on HTML. Actually, with a simple JavaScript wrapper, we can extract names with 100% precision and recall in this case. It's just 4 lines of code. However, we cannot write wrappers for every web page, and in most cases they will not be nearly as simple as the one above. Then, how to extract information from different domains with good precision and flexibility. We saw that wrapper-based methods lack flexibility, and NLP-based methods are much more flexible, but they do not perform well on HTML. At least not if we don't take into account the HTML structure. Our method achieved 94.37% precision and 97.61% recall at the task of researcher name extraction from 149 faculty pages. So let's show it now. Let T be a sequence of tokens, and Y be a sequence of labels attributed to these tokens. Then Y star is a sequence of labels with maximum probability for that sequence of tokens. In fact, with just a few assumptions, this probability can be approximated by the expression below. Check the references at the final of the presentation for the derivation of this formula. This expression can be divided into two parts: the prior probabilities and the conditional probabilities. First, the conditionals. They are probabilities such as the probability that a token is John, given that it's a name, or the probability that a token is John, given that it's a word. They are easy to obtain as long as we have a long list of names and a long list of words. The DBLP database that we used before in our matching strategies provides the first, and the web provides the second. The priors are a little harder to obtain. We'll need a labeled corpus over which you can estimate probabilities for all label sequences with a given window size. In our experiments, the dataset consisted of 149 manually labeled faculty pages. The model was tested through a 5-fold cross-validation. This means that the priors were calculated over 4 training folds and the model was tested on the remaining fold. In fact, with just a few documents we can train a good enough model for most extraction tasks. The model described previously can already achieve precision and recall above 90%, but you can further improve it through the secondary estimates strategy. It consists of enhancing the conditional probabilities with HTML features such as CSS class names, enclosing HTML tags, positioning the DOM tree, etc. On the first time we run the algorithm without the HTML features, we'll be able to extract part of the names, but maybe not all. By looking at the estimated labels, we can create fake training data for that document only, and then estimate conditional probabilities, such as the ones we obtained before. With the estimated HTML features, we can detect names that otherwise would be undetected. Because they share HTML properties like CSS class names or enclosing tag types with other names that were previously detected. These HTML patterns are usually exclusive for that web page, so the feature estimates cannot be generalized. We performed some experiments to test our model. The dataset consisted of faculty pages from 149 universities from 49 different countries, with 11,782 researcher names. All metrics were calculated through the average values of a 5-fold cross-validation run. In the first experiment, we compared 3 different models. The base model has only prior and conditional probabilities. The textual model uses general features such as token length, token incidence, etc. to improve conditional probabilities. And the structural model uses HTML structural features through the secondary estimate strategy to improve conditional probabilities. An asterisk in the table shows metrics that showed a statistically significant improvement relative to the base model. So we can see that the secondary estimate strategy was very successful in improving the model. In the next experiment, we compared 3 different approaches to the best model from our previous experiment. The single matching model matches all tokens that occurred at least one time in the DBLP name list. It has a high recall but a low precision. The composite matching model matches all complete names that occur exactly in the DBLP name list. It has a very high precision but a low recall. The naive Bayes classifier is similar to our model, however it makes a token independence assumption, and it has a performance that is similar to the composite matching model. Our model is the one with the best precision and recall. Finally, our name extraction method achieved 94.37% precision, 97.61% recall, and 0.9596 F measure on a corpus with 149 faculty directory web pages. The model is tuned for the particular problem of name extraction, but we believe this result can be generalized to solve other data extraction problems. And the secondary estimate strategy was successful in further improving the base model. It can also be used with other statistical classifiers since it does not rely on any particular implementation details of our strategy. Check the references for more information. If you want to contact the authors, use emails below.